Okay guys, in this video we're going to start the next section, which is entitled Colligative Properties. However, it's kind of a long section, and so I'm actually going to break it into two parts. And so in this first part, we're going to be talking about different units of concentration that can be used for solutions. In particular, we'll learn about the mole fraction. I believe you've seen mole fractions before in the context of gas mixtures. However, we're going to be applying it to other types of solutions as well. And then we're going to introduce a new concentration unit called the molality. And so we'll be doing some calculations involving these concentration units. And then in a later video, we'll talk about the colligative properties of solutions. And so we'll start with this slide here, where I list different units of concentration, and then the relevant formulas for these concentrations are listed below. So one unit of concentration that I know you've seen before is called the molarity, and I'll just point out that in my notes, the notation that I'm using is C. So this stands for concentration. So molar concentration. It's the number of moles of solute per volume of solution, which is typically measured in liters. And so here's the mathematical formula for that. The molarity is number of moles of solute in the volume of solution. And so I'll just point out one other feature about notation. So suppose that you had 3.0 moles of solute per liter of solution. You'll often see this written as 3.0 with a small upright m, which is abbreviated molar. And it means the same thing, moles per liter. And that's true of some of my assessment materials as well. 3.0 with a capital M is molarity. And what I'm telling you is that the quantity represented by the symbol C in my notes is a molarity. Okay. Another unit of concentration, as I mentioned before, is the mole fraction. And so it uses the symbol X, and the little subscript here, I, refers to the ith component. So if you have 5 components, you would have x1, which would be the mole fraction of the first component, x2, which would be the mole fraction of the second component, and so on. So the mole fraction relates the moles of some solute to the moles of to the total number of moles. And so it's a unitless quantity. You take the number of moles of component I and divide by the total number of moles within your solution. Okay, so that's one way of measuring concentration. Another way that you haven't seen before is the molality. And here we're using a lowercase m to denote the molality. It relates the moles of solute to the mass of solvent. Now it's very specific. It's not the mass of solution, it's the mass of solvent. Also specific is volume of solution in the molarity definition. It's not volume of solvent, it's volume of solution. So these subtle things are, these differences here, they're not, they should not be overlooked. So the units are moles per kilogram, and here's the chemical formula that I'll be using. Moles of solute per kilograms of solvent. We are going to be doing, well, first we're going to learn to calculate molality and mole fraction. Mole fraction's pretty, those are easy, so just using these formulas are straightforward. But then some of the more challenging problems will be converting from one unit of concentration to a different unit of concentration. And for here we're going to need a variety of conversion factors. One conversion factor that we'll use is the tried and true molar mass, which relates mass of compound to number of moles of compound. Okay, so the molar mass. We'll also use the density of a solution, which relates the mass of a solution to the volume of solution. Okay, so that's going to be an important conversion factor. I have a little bit of a mistake here. Whether you use D or the Greek symbol rho for density doesn't really matter. I think I've seen it both ways, so probably it's a good thing I put both symbols on there. One other equation that we'll need that I often forget to write down is that the mass of the solution is equal to the mass of the solute plus the mass of the solvent. Okay, it's easy to overlook that because it's obvious, but nevertheless it's an equation that we will use. You just want to be careful that you don't confuse mass and molality, because those are different things. Okay, so what we want to do in these next set of slides is just to practice some problems. Okay, and so this one is a straightforward one where they simply want us to calculate the mole fraction and molality of ethylene glycol in water. Okay, so we have equal volumes of ethylene glycol in water, and we're being asked to calculate the mole fraction of the ethylene glycol and the molality of the ethylene glycol. Notice they give us grams. Okay, so we have around 2 kilograms of each. And so what we want to do in order to calculate, let's start with the mole fraction. The mole fraction of the ethylene glycol is going to be the number of moles of ethylene glycol divided by the number of moles of ethylene glycol plus the number of moles of water. It's very helpful as you're learning how to do these concentration problems that you practice them, and when you practice, you want to be writing out the definitions of the formulas because that'll help you remember what they are. So that's the mole fraction. To get the molality, so the molality of the ethylene glycol is going to be the number of moles of the ethylene glycol divided by the kilograms of the water. So we need to know the number of moles of ethylene glycol and the number of moles of water. So let's calculate those first, and we'll calculate them separately. All right, that's going to be the mass divided by the molar mass. So we've got 2.22 times 10 to the 3 grams, and we're dividing that by 62.07 grams per mole. I'm going to go ahead and set up the water calculation. And we've got exactly 2 kilograms, not exactly, but 2.00 times 10 to the 3 grams of water divided by 18.02 grams per mole. So now we'll get these numbers here. So I'm getting 35.8 moles. And I'm getting 111 moles for the water. Okay, so now we've got the moles of water. So it's easy. The moles of ethylene glycol, or the mole fraction, will be the 35.8 divided by 35.8 plus 111. And the molality will be that 35.8 moles divided by the kilograms of the water. And so let's calculate these numbers. So notice that the mole fraction is unitless, and the units of molality are moles per kilogram. Incidentally, what would be the mole fraction of the water? Well, you could take 111 divided by the sum of the two, or because there's only two components and the mole fractions of the two components must add up to 1, you could say that the mole fraction of the water is 1 minus the mole fraction of the ethylene glycol. So that would be 0.756. Okay, so you need to be able to calculate mole fractions and molality. These problems, I'm going to look through them very quickly, but I believe they are identical. Mole fraction molality of ammonia in water, mole fraction molality of glucose in water, mole fraction molality of toluene in benzene. So these three problems are identical to the ones that we've just done. The only thing that's different are the amounts that are being combined and, of course, the molar masses of the compounds. But beyond that, these three problems are performed in exactly the same fashion as we've done here. So I'm going to leave those as an exercise for you to try. And we'll look at, let's see if this is a different type of problem. So we have a solution where we're given the molality of methanol dissolved in ethanol, and they want us to calculate the mole fractions of each. So these problems are different, and they're a little bit more complicated. We're being asked to convert molality to mole fraction, and in the follow-up problem, we're asked to convert mole fraction to molality. So let's go ahead and work these problems. So what I like to do is to get the definitions on the board. So let's start with, let's do the molality of methanol. I'll just use a capital M for the method. It's going to get confusing. Let's see. I'll go ahead and write it out just because that would be a little confusing. So CH3OH. That's the number of moles of methanol divided by the kilograms of the ethanol. And what we want is the mole fraction of the methanol. I'm going to try to write this right next to it. So we need the number of moles of methanol, and then you would divide that by, I'm going to put it as in total just to save space so it fits on the screen here. So we're given this, we know that number, and we're being asked to calculate this number. And what I want to point out is that the two equations, they have something in common. The numerator is the same in both. Okay, and so that's the trick to this problem. Okay, so we want to somehow extract the numerator from the molality so that we can use it in the mole fraction. And then we'll have to come up with a way to get the denominator as well. Okay, so we're going to do a little numerical trick here. What we're going to do is assume 1 kilogram of solvent. So if we make that assumption, if we assume that we have 1 kilogram, I should have said of solvent, in this case it's the ethanol. It's a 5 right there. Okay. So if we assume that we've got 1 kilogram of ethanol, we can use that to very easily determine the number of moles of methanol. right? And it's simple. So you take the molality, 0.120. This is moles of methanol per kilogram of ethanol. Well, we've got 1 kilogram. That means we've got 0.120 moles. So this was a very convenient thing for us to do. Assume 1 kilogram, and then the molality that you're given is numerically equal to the number of moles of methanol. So we've just got the numerator of what we want here. Now we need to figure out what's the total number of moles. Well, we know the number of moles of the methanol. To get in total, we need both. We need the number of moles of the methanol, which we have, plus the number of moles of the ethanol. Well, how are we going to get that? Well, we've already assumed how much ethanol we have. So we just need to figure out how many moles are in 1 kilogram. Okay, so we can do that. So let's say the number of moles of ethanol will be equal to 1 kilogram. We'll make it 1 times 10 to the 3 grams. And what are we going to do? We're going to divide by the molar mass, which is given to us as 46.07 grams per mole. So I'm getting 21.7 moles. And so now our mole fraction of methanol is going to be 0.120 moles divided by 0.120 moles plus 21.7 moles. And we get 5.50 times 10 to the minus 3 is the mole fraction for the methanol. How would you get the mole fraction of the ethanol? Well, it's a binary solution. There's only two components. And so the mole fraction of the ethanol is going to be 1 minus the mole fraction of the methanol. So very easy to do that. I'll leave that as an exercise. Okay, so this was converting converting molality to mole fraction. Now in the follow-up problem, we are going to do it the other way. We're going to go from mole fraction to molality of methanol. So we've got the mole fraction of the methanol. I'll write it out again. It's the number of moles of methanol divided by the total. Let's do n total again. And then what we want is the molality of the methanol, which is the number of moles of the methanol divided by the kilograms of the ethanol. So I'll point out again that the numerators are the same. So what we'd really like to do is to have a convenient way of extracting the numerator from the given mole fraction so that we can use that in the numerator for the molality. The last problem indicates how we would do that. It's a little bit different here. What we'll do is we'll assume that we have 1 mole total. That is, we're assuming that the number of moles of methanol plus the number of moles of ethanol, we're assuming that that adds up to 1. So you take the mole fraction and multiply it by 1 mole total, and then that's going to give you the number of moles of methanol. So once we make this assumption, we can immediately write down that the number of moles of ethanol is 0.250 moles. Moreover, we can figure out that the number of moles of the ethanol is simply going to be 1 mole total minus the number of moles of methanol, which is 0.250. So this would be 0.750 moles. Okay, so now we know the number of moles of each component. And we're going to be using the number of moles of methanol in the numerator to get the molality, and we need the denominator. We need the kilograms of ethanol. Well, we've got the number of moles, we've got the molar mass, let's just convert that to kilograms. So we'll say that the kilograms of the ethanol, that's going to be equal to the number of moles of ethanol times the molar mass of the ethanol times 10 to the minus 3 kilograms per gram. So we'll have the 0.750 moles. We'll multiply that by 46.07. That'll be grams per mole. And then we'll divide that by 1,000. And that's going to give us the kilograms. So I'm getting 0.0346 kilograms. And so now we can calculate the molality of the methanol. It'll be the number of moles of methanol, which is 0.250, divided by the kilograms of ethanol. I'm getting 7.22 moles per kilogram for my answer. We could say that this is a 7.22 molal solution. Okay, so you need to be able to convert from mole fraction to molality and back the other way, so from molality to mole fraction. These problems here, I believe they are all identical in the sense that they give you a molality and want a mole fraction, or they give you a mole fraction and they want a molality. So there's no additional tricks here. It's the same approach. This is something that you're going to want to practice, particularly if you are a chemistry major or minor. Here is another problem. These ones are different, and so we're being asked in this problem, for part A, you see that you're given a molality of this compound urea, and you're being asked to calculate its molarity. And you're given the density of the solution. So it's helpful, as I said earlier, to write out the definitions that you have and the definitions of what you want. So we're given molality. So I'm going to write this as MU, where the U stands for urea. This is the number of moles of urea divided by the kilograms of water. Water is the solvent here. That's the molality definition. The molarity definition, so the C, is the number of moles of urea divided by the volume of solution. And that's important, that it's the solution that we're talking about. Notice that the numerators are the same. We'd like to extract the numerator from the molality so that we could use it in the molarity. How do we do that? Assume 1 kilogram of water. That means that the number of moles of the urea is numerically equal to 3.42 moles. Okay, that's going to be our numerator in the molarity. We need the volume of solution. Okay, how are we going to get that? Well, we need the density, right? That's why they give us the density. The density of the solution is the mass of the solution divided by the volume of the solution. And that's what we need. We need the volume of solution. So volume of solution is equal to the mass of the solution divided by the density. The mass of the solution is the mass of the solute plus the mass of the solvent. Okay. We know the mass of the solvent. Since we know the number of moles of solute, we can determine the mass of the solute. We're given the density, therefore we can calculate the volume, therefore we can calculate the molarity. Okay, so we need the mass of the solute. I'm going to put that right here. The mass of the urea is going to be equal to the molar mass of the urea times the number of moles of urea. So that's 60.06 grams per mole. We've got 3.42 moles. We'll just leave it like that, grams. Okay, so plugging in these numbers, we've got 205 grams for the solute plus 1,000 grams for the solvent, dividing that by the density of 1.045 grams per milliliter, and then we'll say that there are 10 to the minus 3 liters per milliliter, and that's going to give us the volume. So I'm getting a volume of 1.15 liters. And then to get the molar concentration, we'll take the number of moles, 3.42 moles, divided by 1.15 liters. .97 moles per liter. Okay, so that's part A. Part B is going the other way. You've got a molarity of 2.00. They're giving us the density of the solution. and they want us to calculate the, this is clearly a typo, it should say molality, not molarity. They've already given us the molarity. We would need to calculate the molality. So it's the same thing. In fact, we've got the same equations as before. The molarity that we're given is the number of moles of urea divided by the volume of solution. The molality that we want is the number of moles of urea divided by the kilograms of water. We want the numerator out, so we will assume in this case we're trying to extract the number of moles from the molarity. So what will we assume? Well, to make things easy, we'll just assume 1 liter of solution. In that case, the number of moles of urea is numerically equal to the molarity. All right, so we've got the numerator. We want the mass in kilograms of just the water, not the solution, just the water. So we still have to work with the density equation. Density is equal to mass of solution divided by volume of solution. We know the volume of solution. The mass of the solution is going to be the mass of the urea plus the mass of the water. So what we're solving for is the mass of the water. So rearranging, we're going to have that the mass of the water is equal to the density times the volume of the solution. That's the total mass, and we'll subtract off the mass of the urea. The mass of the urea is going to be equal to the number of moles times the molar mass. Okay, the molar mass is that 60.6 grams per mole. 60.06 times 2. So we'll take it as 120 grams. The density of this solution is 1.029 grams per milliliter, and we assumed 1,000 milliliters, 1 liter. And then we'll subtract off from that, we'll subtract off the 120 grams. That leaves us with 909 grams, which is 0.909 kilograms. So when we go to calculate the molality of the urea, we'll take the 120 grams, sorry, that's not right. We'll take the 2 moles and divide that by 0.909 kilograms, and we get 2.20 moles per kilogram. Okay, so a slight difference between the molarity and the molality. They're not quite the same unit. The next set of problems are just the opposite, or they're the same thing, but just for different compounds. So here you've got a molality of potassium chloride. You're being asked to calculate the molarity. Here you're given the molarity of a lead 2 nitrate solution, and you're being asked to calculate the molality. So it's the same problems, just different compounds, different molar masses, but the procedure is the same. Well, I'm going to go ahead and stop this video here, and we'll pick up with the colligative properties on the next one.